Welcome, good morning. Hope you have gone through earlier lectures under multivariate linear regression. Today we will continue with model adequacy tests. Today we discuss several tests like Bartlett test, Rao test, Pillai's trace, Hotelling-Lawless trace and Roy's greatest root.
Problem lies where? Problem lies these lambda, but the way you are making, these are all generalized variants. When you take the determinant of a covariance matrix, these are generalized variants, and this lambda is a point estimate. Getting me? Point estimate. What is the guarantee that this point estimate is giving you that what you want exactly? There is uncertainty. So, we require to know the interval estimates. So, as a result, what is required? We require to know the distribution of what? Distribution of lambda. This is very, very important, correct? But lambda computation is complex. You see that so much of, first of all, SSCP matrix, that full model, reduced model, then if it is P is very large, Q is also large, then in that case what will happen? Complexity is huge. You cannot get straight cut that distribution for lambda, but researchers, particularly statisticians, they have worked on it and they found out that lambda in different transformation was made for Wilks lambda and some distributions were found out. The two important tests or distributions was given by, one is Bartlett, I think BARTLETT, Bartlett test, and another one is Bartlett test and Rao's test. These are all likelihood ratio test. So, what is Bartlett test? How do you compute Bartlett test? Bartlett test says that you create one statistics which is minus m log base E lambda log S B lambda. This is one statistic created where your m is a multiplier, m is the multiplier. This value is n minus p minus 1 minus q plus 1 minus m divided by 2. Okay. So, you know what is n? Total number of observations. What is p? Number of x variables. What is q? Number of y variables. What is m? That we are saying beta m under H0, beta m equal to 0. So, that m variables you have dropped, correct. So, under this condition, if you say this one, then these statistics, that means minus m log lambda, this follows F distribution, and also it follows chi-square distribution under certain conditions. So, chi-square distribution, that one is given by Bartlett. Yes, it can be approximated to F distribution also, but chi-square distribution, that m with mq degrees of freedom. So, m is number of variables dropped from the independent side, q is the number of y variables. So, this follows this distribution. Now, what you will do then? You know that this chi-square distribution looks like this, and our this minus m log lambda, this follows chi-square distribution. So, for some value, that is the rejection region. So, you find out what is this value. is minus m log lambda is falling somewhere in the rejection region or not. So, this point, the critical value is your chi-square. If I say this is alpha, then chi-square mq alpha, this is your critical value. Now, you will reject H0 if minus m log lambda greater than equal to, you can write chi-square mq alpha. Okay. Now, second one is Rao's statistic. In 1952, Rao has given similar statistics for Wilks lambda. His statistics is this one, that the statistics what it created, it is 1 minus lambda to the power 1 by q divided by 1 by q into mq plus 1 minus mq by 2 divided by mq. This is the statistic. Okay. Where m already you have computed, m is the multiplier, earlier you have computed m. So, m we computed like this, this is our m. So, that m multiplier. What is q? Q is a quantity which is q square, small q square plus m square minus 4 divided by small q square plus m square minus 5 whole to the power half. This is given by Rao. Okay. So, please remember, if qm equal to 2, this quantity q becomes 0, capital Q becomes 0. If small q into m equal to 2, then q equal to capital Q equal to 0. Under such condition, you have to consider q equal to 1, unity. Other cases no problem, fine. So, you first find out these statistics. So, 1 minus lambda 1 by lambda to the power 1 by q by lambda to the power 1 by q, 1 by q. Okay. This is not y, this is 1 by q, mq plus 1 minus mq by 2 by mq. This quantity q will be computed like this. This follows F distribution with mq and capital M capital Q plus 1 minus mq by 2 degrees of freedom. So, what will be your, when you reject null hypothesis? If I say this statistics, this total value is D, then you reject H0 when D must be greater than equal to F mq m capital Q plus 1 minus mq by 2 into that one alpha value, this not into, this is the alpha probability value. Okay. So, when you are using this ratio, likelihood ratio statistics, these two statistics are useful, fine. So, when you, if you use SPSS, SAS or some other program like Minitab, you can ask Bartlett test, Rao test, but Bartlett test is available. Rao test, I do not think that Rao's test, I have not seen, it may be available. Okay. Now, question is, these tests are very sensible, in the sense, what I mean to say, for example, Bartlett's test, you say that chi-square distribution is followed, but chi-square distribution under what condition? It says that if your sample size is small, Bartlett test will not work. So it says that n must be greater than p plus q plus 30. What is p? P is number of IVs, q is number of DVs, and 30 plus 30. This is the case. This one is basically developed by Sage Job, SCHAT ZOFF, SCHAT ZOFF in 1936. Prove that for Bartlett test, this is the requirement, then only the chi-square distribution will be followed. I think you understand. But there are other tests not based on likelihood ratio. Getting me? There are other tests which are not based on likelihood ratio test. These other tests are interestingly, suppose in ANOVA we know that F equal to MSR by MSE, that means MSR minus F MSE, this is 0. This is 0. Now its equivalent or analog in multivariate domain. Okay. So you all know that your multivariate domain you will not get this scalar. MSR, MSE all are scalar quantity in MLR, multiple linear regression, but MBLR you will not get this. You are getting SSCP matrix, and under H0 beta m equal to 0, we found out two things, that we said that under H0 you found out this SSCP, and under full model you found out this one. Okay. Now you can create one statistics which is basically R, similar to R I am using because of this regression. That means the regression, this can be like this. You can create like this, R equal to this. That means what is this? This difference, how much the m variable you are dropping, that is contributing. You are testing H0 here also. In ANOVA also you test H0 here, and then you through F test you say yes, some of the variables are contributing, that is in MLR. But in MBLR also, if I say that what is this? This R is the difference between this and this multiplied by the number of observations, and if I say that E equal to N, that full model. Getting me? Now if I create like this, now what is happening? This R can be similar to MSE, and E can be similar, R can be similar to MSR, E can be similar to MSE. But as they are in the matrix domain, they are equivalents in terms of your scalar domain, you have to take determinant. So that is why what happened, that is statisticians have developed that if you take this determinant equal to 0, then you will get very interesting roots, characteristics. What is this? This is basically, if I write, it is nothing but n epsilon 0 cap sigma 0 cap minus sigma 0, that is R, minus lambda n sigma 0 sigma cap. This one, this is R minus lambda E, this is the matrix. Now if I take determinant here, so ultimately what is happening, this n will go out, n will be cancelled because this you are putting is 0. So this one is 0, this is the characteristics equation. Getting me? And lambda will give you eigenvalues. That you know. Now this eigenvalue lambda, how many eigenvalues will be there? It all depend on the that what is this order, what is this order of this matrix, this resultant, this matrix, that is what is the order of this matrix. We always think of the determinant mean full order, full rank matrix is required to be. Now suppose that we say that the order is basically S, which is minimum of Q and P minus M. That will be the order. Q is number of dependent variable, P is number of independent variable, M is number of dropout variables. So this is number of dropout variables. Okay. So then once you solve this equation R minus lambda E this equal to 0, you will be getting this will be S power, that power will be because there are S roots will be there. These roots are basically lambda 1 greater than equal to lambda 2 greater than equal to lambda S. These are the roots, and you will see that these roots when you do this eigenvalue decomposition of matrix similar this one. So that ultimately what you will find out? You will find out that P roots, or here it is S roots, and they will be that first root, first one is the maximum one followed by next mesh like this. Okay. So using this property there are several statistics developed. Several statistics were developed. For example, you will find out that Wilks lambda will become like this. Wilks lambda will become like this, equal to this. This is nothing but determinant of E. I think E you can understand now the way we have defined, divided by E plus R. Are you getting some clue with maneuver? Wilks lambda is SSCPE divided by SSCP between plus SSCPE. Now this between means what happened? Population contribution. So it is similar to regression contribution error. So that determinant of this divided by determinant of this we have computed there. So this one, when you define in terms of your eigenvalues, it will be like this: multiplication j equal to 1 to S 1 by 1 plus lambda j. Okay. So that means what you require to do, you require to find out this equation, then find out the lambda values, you will be able to find out this Wilks lambda values also, small lambda, capital lambda. This definitely follows certain distribution, and in all cases F distributions are approximated. Here some other distribution like chi-square we have seen, Bartlett has given chi-square distribution, Rao has given F distribution for this Wilks lambda. Apart from this, there is another statistics which is known as Pillai trace. Pillai trace statistics. What it is done? It takes V equal to trace of R into R plus E inverse. So these are just variant, almost similar under certain condition, but to get the different benefits it is done like this, and this one will become j equal to 1 to S lambda j by 1 plus lambda j. You will get also another statistics here which is Hotelling-Lawley that trace, Hotelling-Lawley's trace, another one. That what is Hotelling-Lawley's trace? Hotelling-Lawley's trace is H, which is trace of R E inverse. This one is nothing but lambda j, j equal to 1 to S. there is another statistics which is known as Roy's greatest root. Roy's greatest root G. So that G is taken only the first eigenvalue, this one. So all software including SPSS, SAS, they report all those statistics. So now what is this? You please understand, under H0 these statistics are developed. So if that means most of the time we will find out that F distribution. Now if this value is more than or equal to the cutoff value from F distribution, so what you will do then? In that case you reject the null hypothesis. That means the set of x variables m in number, what you have rejected, that is not correct. Now if I consider m equal to 1, that means individual variables at a time you are testing. So for every variable you test and then see that whether it is contributing or not. Like in ANOVA case, individual variable SS you have identified. So with this I want to go to the example. This is the Statistical data. So intercept, see Pillai's trace, Wills lambda, Hotelling trace, Roy's largest root, all those values are computed, their F test is taken and then significance level is very high. That means intercept is there, it is contributing. Absenteeism similarly, is it significant? Not. That 5% level it is not significant, but little more than 10% level it is significant. Now you can drop this variable if you think so, but if you think so then on 10% level it is required, fine. Then you say breakdown for every stress. Interestingly, everyone, Pillai, Twill, Hotelling T-square, everyone is giving the probability level almost equal, but the value is differing and the degree of freedom will remain same, error degree of freedom also remains same, and this is the case. So what is in nutshell what we are saying? We are saying here that you are going for model adequacy test by similar F test like in case of multiple regression, that ANOVA, but here also you are doing this and you are finding out that yes, some of the variables are contributing, so multivariate regression is required. Now go to the next one. So this is the your total sum of squares under that profit under sales, and you see R square like univariate R square, that multiple regression R square. For first one it is 0.924, for the second one, that means for profit 92%, for your breakdown, not breakdown, this is sales 86.6%. Okay. And also you have tested the significance level here for different intercept, for absenteeism, for breakdown, getting me, and their significance level, everything is tested. Once you accept this, you have to go for diagnostics similar to your MLR. This diagnostics is required, and almost all the software they give you this type of plots. These plots are basically, I say, residual plots. Okay. Now see the residual plots. So observed versus predicted, it should be straight line linear. Now observed versus, if you see observed versus this one is, this is observed predicted, fine. Now if you go by residuals versus predicted or residuals versus observed, that should not give any trend, it should be random, it is coming like this. Okay. So predicted versus residuals also, that should also become random. So this for profit this is the case, for sales also similar thing we are getting, and in fact from this figure you are not getting any unusual observation. In summary, when you go for MBLR, you see that when you have more than one dB, both the more than 1 dB and all the dBs they occur simultaneously. Then IVs are same, means independent variable are same affecting different dBs. Estimation, this is the condition when you will go for this. The multivariate normality, that covariant structure equal and other things, that assumptions you have to test. Then estimation, from estimation point of view, estimation similar to MLR. Model adequacy test is complex because you are going for likelihood ratio test, and there are different tests identified, that Pillai stress, Willis lambda, Roy's greatest root, and then Hotelling-Lawley, all those tests are there. Several multivariate tests, that is why this is used. IV should be truly independent. Other assumptions also equally important, does not give much advantage over MLR, but protect against error handling. So, if you go separately for regression estimate point of view, no problem, but adequacy test point of view there will be problem if you go for separate MLR, getting me. So, this is the advantage, and I think when you have multiple y variables and you are sure that they are following, you are able to prove that assumptions are not violated or reasonably following, then what you have to do, it is better you go for MBLR, multivariate regression first, and then you test through different tests, you are finding out yes these are contributing, then you will, if you go for single MLR, that means multiple linear regression instead of MBLR, absolutely no problem. It is similar to that ANOVA and that analogous is MANOVA. You must go for MANOVA when you have more than one dependent response variable, and then you see that collectively they are affecting or not. If not, go for ANOVA, no problem. So, similarly MBLR and this. So, this suppose this MANOVA and MBLR, all those things comes under general linear model. If you go to SPSS or SAS, there will be one link GLM. Okay, any question? Thank you very much.